Welcome back, everyone. The topic for this video is solids and lattice structures. So just remember that solids, of course, are going to be closely packed together, though they can vibrate between the atoms. They're incompressible and they're going to retain their shape and volume. And of course, you have the difference between crystalline solids and amorphous solids. So crystalline solids are going to be very organized, and amorphous solids are going to have no pattern over a significant distance. So some examples of crystalline solids are going to be your table salt and diamonds. Amorphous solids, things like your plastic and glass. So we're going to talk about four different types of solids. You have ionic solids. Of course, remember those are going to have a cation and an anion. That's a metal and a nonmetal. Many of your ionic crystals are going to have high boiling points. They're going to be hard and brittle, but they're not going to conduct electricity unless they are molten or dissolved in water, where those ions are free to move. Now, metallic solids, these are typically considered a sea of delocalized electrons. They're going to be hard and strong, and because of that sea of electrons, they're going to have high electrical conductivity, metallic luster, and they're going to be malleable. The melting points for metallic solids can vary widely, so they're not always considered high like your ionic solids. And then the other two types, those are going to be for your nonmetals. So covalent network examples are going to be things like your diamond and silicon dioxide, which is pictured to the right here. They're characterized by their hardness, strength, and high melting points. And then molecular solids, we have carbon dioxide here as an example. You also have table sugar and ice. And so the strengths of these attractive forces, they're going to vary widely, and so you're going to see a wide range of melting points similar to your metallic solids like we saw before. Okay. So majority of this topic, we're going to focus on our unit cells. So within a crystalline solid, whether it's a metal or not, you're going to find these repeating units, which we call unit cells. And the lattice points are going to represent locations of atoms or ions within this unit cell. Now, the simplest unit cell that we'll talk about is what we call the simple cubic structure. And so we call it the simple cubic unit cell. So a simple cubic unit cell is going to be when we have an atom at basically each corner of the cube. So these are going to be very inefficient in terms of their packing. They only fill about 52% of the volume of the container. And we can determine the coordination number for each type of unit cell based on the number of other particles that are in contact with a specific atom. So for example, in the simple unit or simple cubic unit cell, we have a coordination number of 6. And so that's shown up here in the top right-hand corner. You can see how if we look at this atom in the center, you're going to have contact with an atom above and below, and then 4 atoms surrounding it at its surface. So when we look at the diagrams down in the bottom right-hand corner here, we can see that the corner of each atom is going to be located in that unit cell. And so here is when we cut out those pieces of atoms, you can see that you've got 8 atoms. Each corner of that cube has just a corner of the atom inside of it. And that corner is worth 1/8 of an atom. Okay, and you would find out that each atom, that it's located in 8 unit cells. So if we look again up at this top red atom here, you can see that there are 4 cubes on top, right, and 4 cubes below. Okay, so if you count those up, you've got that atom occupying a total of 8 cubes, and so that's where you're getting 1/8 of the atom located in one cube or one unit cell. So because of this, if we want to calculate the total number of atoms located in a simple cubic cell, we're going to look at all the corners, right? And a cube has 8 corners to it. So if each corner has 1/8 of an atom, and you have a total of 8 corners in a cube, so 8 atoms at 1/8 apiece, then overall you have 1 atom located in a unit cell, right? 1/8 corner pieces and 8 of them to give you a total of 1 atom. If you're looking at the mass of a unit cell, it's going to have the mass of exactly 1 atom. And then the edge length of a simple cubic unit cell is going to be 2 times the radius of the atom. Okay, and again, we can see that in the picture here. As we go across, you're basically going to have 2 radii that come into contact with each other for an edge length of 2r. Now, the second type that we're going to look at is the body-centered cubic. The body-centered cubic cell is going to be one where we have an atom located in the center, as well as those 8 atoms on each one of the corners. So the coordination number for a body-centered cubic is going to be 8. Right, and again, that's because if we look at this center atom, it's touching 8 different atoms around it. So it has a coordination number of 8. The edge length is a little bit more complicated, but it's 4 times the radius of an atom divided by the square root of 3. And then if we want to look at the total number of atoms in the unit cell, so this is for a body-centered cubic, we've got in the corners, right, 1/8 of an atom, and there's 8 corners. Okay, so again, that comes out to be 1 atom. But now we also have in the center, we have an atom that is fully located in that unit. And so we've got 1 atom there as well. And if we total these up, you get a total of 2 atoms. So if we were to check the mass of a body-centered cubic, we should find that there are a total of 2 atoms in that cell. Okay, and these are going to be very important, these numbers of 1 atom in the simple cubic, 2 atoms in the body-centered. We're going to need this when we look at calculations at the end. Okay, and then the last type of unit cell that we're going to talk about in this class is the face-centered cubic. So the face-centered cubic is a unit cell with atoms at all corners and all of the center of each face. So when we look at an atom that's on the face of a cube, that's going to take up 1/2. So each one of those is 1/2 of an atom. Okay, face-centered is going to be the most efficient packing, and of course body-centered would be somewhere in between the two. Atoms are going to touch the corner, and you're also going to touch the face of all of the diagonals. So the coordination number here is going to be 12, and the edge length is equal to 2 times the square root of 2 times the radius. And so if we want to calculate the total number of atoms in a face-centered cubic, we still have the 8 atoms in the 8 corners, right? So if we look at the corners, we've done this enough. The corners are going to be a total of 1 atom, right? It's going to be 1/8 times 8. And then we've got the faces. So if you count up all the faces of a cube, you should count that there's a total of 6 faces, and each one of those is going to be half an atom. Okay, so we have 1/2 times the 6 atoms for the 6 faces of a cube. And 6 divided by 2 will give us 3 atoms. Plus the 1 atom from all the corners gives us a total of 4 atoms. So the mass of a face-centered cubic cell should have a mass of 4 atoms. Again, very important for our calculations. Okay, so for the rest of this video, we're going to go through several practice examples looking at the math behind these 3 different types of unit cells. So, typically they are going to have to talk about the density. And remember that density is going to be equal to mass divided by volume. Okay, and I'll go ahead and change my pen color. So when we're talking about the mass of a unit cell, we're typically talking about the number and type of atoms. So remember from Gen Chem 1, and you might have to go back and refresh this, but if you have a certain number of atoms, you can figure out the mass, right? So we can either go from number of atoms and figure out the moles, right, using Avogadro's number. And we can go between moles and the mass in grams, and this is where we would use our molar mass from the periodic table. Okay, so you may need to go back and review those topics. And then the volume is going to come from either the edge of the cube or the radius of the atom. Right, because for each type of unit cell, we know how to calculate the edge length from the radius of an atom. And of course, once we know the edge of a cube, remember that the volume of a cube is just going to be the length or the edge cubed. Okay, so with this information, let's see what they give us and what we're looking for. So lead has a face-centered cubic lattice with all atoms at lattice points and a unit cell edge length of 4.950 angstroms. What is the density in grams per centimeter cubed of lead? Okay, so if they're asking for the density, that means that we're going to have to figure out both the mass and the volume. Okay, so let's just start out with that mass. So remember, mass in grams means that we have to first know how many atoms that we have. And to determine the number of atoms, we've got to know what type of unit cell that we have. And that is a face-centered cubic. So if we look back at the face-centered cubic, just remember that a face-centered cubic has 4 atoms. That's why these numbers are important, the total number of atoms in a unit cell. So because it is a face-centered cubic, we know that we have 4 atoms of lead. Okay, so we can convert that into moles and then convert that into grams to get our mass. So to go from atoms to moles, we're going to need Avogadro's number. Remember, Avogadro's number is 6.022 times 10 to the 23rd atoms per 1 mole. So that means that we're going to have to flip Avogadro's number, put the 6.022 times 10 to the 23rd on the bottom. And remember, that is atoms, or any type of particle for that matter, per 1 mole. Okay, so atoms cancel, and we're left with moles of lead. And now we can convert to grams using the molar mass. So you would have to go to the periodic table and see that the molar mass is 207.20 grams per 1 mole. Okay, so now moles will cancel out, and we're left with the grams of lead that we have. And 4 is, remember, that's a counting number, so that's exact, and that's going to have infinite sig figs. And anytime you see me write a capital SF, that just stands for significant figures. Okay, so our sig figs must come from either Avogadro's number or from the molar mass. So we will keep 5 digits for now, but we're going to be limited by 4 digits based on that edge length at the end of the day. Okay, so if we keep 5 digits, that will be plenty. So we get 1.3763 times 10 to the negative 21st grams. Okay, so that gets our mass. And now we need to find the volume. So remember, volume is going to be based on that edge length, and volume is the edge length cubed. So the issue is that we need to find the density in centimeters cubed. So it's easier if we go ahead and convert that edge length into centimeters before we cube it. Okay, so we're going to take that 4.950 angstroms. And we know that 1 times 10 to the negative 10th meters equals an angstrom. And we're going to consider that exact by definition. So 1 angstrom will go on the bottom, and 1 times 10 to the negative 10th meters will go on top. Angstroms will cancel. And then we need to convert to centimeters. Remember, there's 100 centimeters for every 1 meter. So 100 centimeters on top, or 1 times 10 to the second, depending on what you memorized, and 1 meter on the bottom. All right, so we are just getting that edge length in centimeters, and that comes out to be 4.950. We're keeping that 0 because it is significant, and we want to remind ourselves of that, times 10 to the negative 8th centimeters. Okay, and then we just need to cube it, so I'm going to take that number, raise it to the 3rd power, and I will get a volume that is equal to 1.212, and we're going to keep 1 extra digit until we're done, so that's the 9, times 10 to the negative 22nd power, and centimeters cubed. Okay, so we have our mass up here, right? Mass equals, and we have our volume. So density, we're just going to divide the two. 1.3763 times 10 to the negative 21st grams divided by the volume of 1.2129 times 10 to the negative 22nd centimeters cubed. And we started out with 4 sig figs from the beginning, so we're going to end with 4 sig figs and get 11.35 grams per centimeter cubed. Okay, so again, one important fact that we needed was the face-centered cubic, knowing that that is 4 atoms to get us started. Then we can convert to mass using our Gen Chem 1 topics of Avogadro's number and molar mass. And then volume, remember volume is just that edge length cubed, and we've got to get that edge length in centimeters before we cube it. Okay, second example. Barium metal has a body-centered cubic structure. Calculate the edge length of a unit cell in picometers. Okay, and we're also told that 1 meter is equal to 10 to the 12th picometers. So again, we're going to need that density equation. Density is equal to mass over the volume. And we're asked to calculate the edge length. So remember that the volume is the one that has to do with the edge length. So we're somehow going to have to use our density and find the mass in order to calculate that volume and then backtrack to the edge length. Okay, and mass is going to come from the number and type of atoms that we have. So again, that's where we have to look and see that we have a body-centered cubic. And remember, body-centered cubics have 2 atoms. Okay, so we're going to start out with those 2 atoms. It's also important to know that we have barium. Okay, so we're going to need the molar mass of barium from the periodic table. Take those 2 atoms, divide by Avogadro's number, 6.022 times 10 to the 23rd atoms per 1 mole. Okay, and then multiply by the molar mass of barium on that periodic table should be 137.33 grams per mole. And again, infinite sig figs here, but we know the density is going to be 3 sig figs, so we can keep this down to 4 sig figs and have plenty to prevent round off errors. So we've got 4.561 times 10 to the negative 22nd grams. Okay, now we have the mass and we have the density. We can use dimensional analysis to get those grams to cancel and find the volume. You can also solve the density equation if you prefer, but I like to take that mass, the 4.561 times 10 to the negative 22nd grams that we just calculated, and multiply that and decide whether I need to keep or flip that density. So I'm doing, just a simple one-step unit conversion where the density needs to be flipped. So the 3.51 grams will go on the bottom, and that's per 1 centimeter cubed. So grams cancel, and I'm left with a volume in centimeters cubed. Okay, that should give us, keeping at least 4 digits, 1.29. So 1.299 times 10 to the negative 22nd centimeters cubed. Okay, that's our volume, right? And remember that volume, we're trying to find that edge length. So volume is equal to the edge length cubed. And so if I want to find the edge length, then I've got to take the cubed root of both sides. Right, so the length is going to be the cubed root of the volume. Okay, so I will plug that in. Cubed root of the 1.299 times 10 to the negative 22nd, and I get back 5.07 times 10 to the negative 8 centimeters. And I know 3 sig figs from density, and I'm almost done, so I'm going to go ahead and round that off to 3 sig figs for my answer, because the last step is to convert from centimeters to picometers, okay? And that's just going to change the magnitude, basically. So we have our length in centimeters, and we know that there are 100 centimeters in 1 meter. Centimeters cancel, and then we can take the 1 meter equals 10 to the 12th picometers. So 1 meter, and on top 10 to the 12th picometers. And so our meters cancel out, and our length is equal to 507. Okay, so I wanted to add a second part to this question. So I'm going to rewrite that length really quick as 507 picometers. And then I want to ask the question of what is the radius of an atom? Okay, so if you're ever asked to use the radius or to find the radius when you're given the edge length, remember that you've got to go back for a body-centered cubic structure and find the equation. So for body-centered cubic, remember that the edge length is equal to 4 times the radius divided by the square root of 3. So that length of 507 picometers should be equal to 4 times the radius divided by the square root of 3. And so we can solve this equation, of course, by taking 507 picometers and multiplying by the square root of 3 over 4 to get our radius back. And so that should be roughly 220 picometers. Okay, so just keep in mind length 507, radius 220. Okay, so let's try another example. So in this example, a metal has a body-centered cubic lattice with a unit cell edge length of 2.866 angstroms. We're given the density. What is the mass of an atom? Okay, so again, we always know density is equal to mass over the volume. Of course, they give us the density, and so we've got to find that volume in order to multiply density and volume to get the mass. So if we start out with the edge length, remember that density is in centimeters cubed, so we're going to have to take those angstroms and convert them into centimeters. So if we start out with the edge length of 2.866 angstroms, we're going to have to multiply by the 1 times 10 to the negative 10th meters for every 1 angstrom. The angstroms will cancel, and then we can multiply by the 100 centimeters over 1 meter. Okay, so that should give us 2.866 times 10 to the negative 8th centimeters, and that's the edge length. So if we want to find the volume, we're going to have to cube this, right, to get the volume. So the volume of the cube, and I want to be very specific here because that's going to be important. The volume of the cube itself is going to be equal to 2.354 times 10 to the negative 23rd cubic centimeters. All right, now if I want to find the mass of the cube, so remember, volume times the density will give you the mass. So mass is equal to the volume that we just calculated, 2.3, and I'm going to write this again, mass of the cube, okay? Mass of the cube is equal to 2.354 times 10 to the negative 23rd. And then multiply that by a density of 7.87 grams per 1 centimeter cubed. So centimeter cubed cancel. And we need, again, 3 sig figs is the least number of sig figs, but we keep an extra until we're done. So 1.853 times 10 to the negative 22nd grams, and that is the grams of a cube. Okay, but they're not asking for the mass of the cube, right? They're asking for the mass of an atom. So that's again when we have to go back to the fact that a body-centered cubic lattice contains 2 atoms. Right, so the mass of a cube is equal to the mass of 2 atoms. So if we want to find the mass of a single atom, we've got to divide that mass of the cube. We've got to divide it by 2, right? So we'll take that 1.853 times 10 to the negative 22nd grams and divide that by 2 to get our final mass of a single atom. Now we can finally round it to 3 sig figs, so that's 9.26 times 10 to the negative 23rd grams. Okay, so for all of these, again, you're probably going to have to, at some point, use the number of atoms based on the type of unit cell that you have. So just keep in mind, if you hadn't used that 2 yet, you probably should use it somewhere. So, last example for this topic, a metal, sorry, that's the same question. There we go. Gallium forms crystals where we have a density of 5.91, whose unit cell has an edge length of 2.696 angstroms. What type of lattice does gallium have? Okay, so again, if they're asking what type of lattice, they're basically asking how many atoms, right, in a unit cell. And the reason we can phrase it like this is because if it's a simple cubic, that's going to be 1 atom, body-centered is 2 atoms, and face-centered is 4 atoms. So in order to determine what type of lattice that we have, we can determine the number of atoms that we have in a single cell. So we're given the edge length, and of course remember density equal to mass over the volume, and so the mass is going to eventually tell us the number of atoms that we have, because we can take that mass, convert it to moles, and convert it to the number of atoms at the end of the day. So we need to first find the density and the volume, multiply those together to get that mass. We have the density, we need the volume, and we're given the edge length. So we're going to take that edge length and figure out the volume, of course always in centimeters cubed, so 2.696 angstroms. Okay, and we kind of know the pattern here. We're going to multiply by 1 times 10 to the negative 10th meters per 1 angstrom, and then multiply that by 100 centimeters per every 1 meter. And notice how each time, as long as we're starting out with 1 digit to the left of that decimal, that we're always getting times 10 to the negative 8th, because it's negative 10th times 100, which is times 10 to the negative 8th. So this is 2.696 times 10 to the negative 8th centimeters. And we've got to cube that because that's our edge length, and we're looking for the volume. So our volume will be equal to 1.960 times 10 to the negative 23rd centimeters cubed. We've got the volume and we've got the density, so let's multiply those together. 1.960 times 10 to the negative 23rd. And I'm not too worried about sig figs for this question, because if we're asking how many atoms, at the end of the day we really only need 1 sig fig, which it should be infinite if we're counting. So again, sig figs not very important for this calculation, so you could shorten them if you wanted to. So we got this volume in centimeters cubed, and multiply by the density of 5.91 grams per centimeter cubed. Centimeter cubed cancels, we're left with those grams, and that gives us the 1.1, we'll just kind of round this off a little bit, 1.16 times 10 to the negative 22nd grams. Okay, and then last step, of course, is using that molar mass in Avogadro's number. This time we are going backwards. We're going from grams to atoms. So we start off with the 1.16 times 10 to the negative 22nd grams. And we've got to use the molar mass first to get the grams to cancel. Remember, you've got to flip the molar mass so that it's on the bottom. And we've got gallium. So gallium on the periodic table is 69.72 grams per 1 mole. Grams cancel. And then Avogadro's number, we're going to multiply by it this time, 6.022 times 10 to the 23rd, and that is atoms per mole. Moles cancel, left with the number of atoms, and when we calculate this, it is going to be roughly 1 point and then several zeros. So we're looking at 1 atom. Okay, and so 1 atom, of course, is that simple cubic unit cell. Okay, so that wraps up this topic, and I hope this helps.